Okay, thank you very much. And I'm Masahiko Yamada from Osaka University. Let me first thank the organizers for inviting me this very nice opportunities and giving me the time to introduce a very recent new results. And my title is SU for Material, Emergence and Developments, but I mostly talk about my numerics. And let me first introduce the collaborators of this work. The first part, sorry, the first part of the talk is with my boss Satoshi Fujimoto sensei, and the second part of my talk is done with Carlo Penz in Hungary and also Frank Bormann in Munich. And the first part is already accepted in publication in PLB with editor suggestion, and the next talk part will appear very soon. I actually first, after PhD, getting PhD, I first applied for Frank Bormann's group in Munich as a postdoc and accepted. And after that, I also have a chance to apply for the assistant position in the Fujimoto group, and then I decided to stay in Japan, but eventually I worked with both of them, so now everyone is happy, and eventually it's okay. This is my position, and this is the outline of my talk. And first introduce the notion of SU4 and the notion of F34, and then move on to the numerics part. First, let me introduce the finite temperature calculation, and the next to the ground state calculation and the summarize. I'm a computational physicist, but my style is a bit different from others because I first choose the problem and then decide which method to use. So I changed the methods time to time, and this time I will use CTPQ method and the DMRG. Yeah, let me first give a very overview of the Kitaev materials, but already this was nicely reviewed by Takagi sensei. So I just quickly review this material. And quantum spin leaks had long been a kind of vague notion, even theoretically, but the first rigid formulation based on the exact solution was given by Kitaev in 2006. And this is called the theory of Kitaev spin liquid. And the Hamiltonian is already explained, so I won't repeat, but this exotic Hamiltonian can indeed realize the quantum spin liquid state exactly. And also, more importantly, after the discovery of candidate materials like lithium iridate or ruthenium trichloride, this eventually becomes one of the most important fields in quantum matter physics because of these exotic properties coming from Majorana or half quantization, blah blah blah. So this is very nice. But what I want to talk about is what is the next Kitaev, or the what is eventually how to say take over this kind of field. So that's I want to talk about, and of course the physics of Kitaev are already discussed intensively in D5 material, but we move on to the different materials composed of D1 system, D1 electrical system, and I call this type of system SU4 materials, and we kind of more intensely promote this thing. And in 2018, I wrote a paper with George Jackery, Oshikawa sensei, to propose that the D1 electric system with a strong spin coupling can realize another type of quantum spin liquid with a very high symmetry of SU4. SU4 is symmetry higher than the SU2, and what I found in that time is that if you write down the effective Hamiltonian for the D1 material like alpha silicon trichloride, then eventually the low energy effective theory or effective Hamiltonian potentially has a large symmetry called SU4. And also there at that time, I found a very old chemistry paper claiming that this honeycomb material can be realized. So, now this is a very nice playground for new physics based on this new symmetry of SU4. And let me quickly introduce the SU4 Heisenberg model instead of SU2 Heisenberg model, which was intensively discussed in this workshop. And the SU4 Heisenberg looks like this formula. And the simple form is left-hand side, just H equal sum of Pij. Pij is the so-called swapping operator of SU4 spins, which means that it's just like Heisenberg model. Just swap to neighboring states or neighboring sites, swapping the for color and exchange. That's the essential meaning of the Hamiltonian. And of course, this has a SU4, complete SU4 symmetry. But also, we can write this down in a more conventional way, which is the right-hand side. And if you separate 4 SU4 states into 2 spin degrees of freedom and 2 orbital degrees of freedom, spin degrees of freedom are written by SI operator, and orbital degrees of freedom are written by TI operator, which has a spin half. Then the model can also be written by the right-hand side. The coefficient is important. Only 2, 1/2, 2, 1/2 has the exact SU. Yeah, right.
So actually, I have a question. So if you go to the previous slide, what you showed us is because of crystal thin and then synovium.
Yes.
The low energy sector is formed of 4 states.
Right.
Presently, J equals 3/2.
Right.
But this is not a sufficient condition to claim that there is full SU4 symmetry.
Right.
In general, you have spin orbital interaction
That
break the SU4 symmetry in a given crystal lattice.
Right. Yeah, completely right.
So are you saying that for this material you have perfect SU4 symmetry, or is this a sharp transition between reality, which is this, and then the toy model, which has full SU4 symmetry?
This is a very good question, and this is something done in this PR paper. But what I found is that, of course, the effective Hamiltonian of the J3/2 is anisotropic, not has the form of SU4. But what I eventually realized when I take the lambda infinity limit first, and also we use some gauge transformation, then we can somehow recover the SU4 symmetry in the limit of lambda infinity.
The only thing lambda infinity buys you is that it's in two states.
Yes. No. In addition, the lambda infinity limit is important to get the exact gauge transformation, which can transform the anisotropic Hamiltonian to the completely symmetric SU4 symmetric Hamiltonian, which was the thing done in this paper. Thank you very much. And
whatever. I mean, this is a surprising statement.
Yes, that's right. That's right.
Okay, but we don't need to read that paper and then we know.
Yes. Because the time limitation, I cannot have time to explain why lambda infinity limit actually gives this SU4 symmetry, but that's what I did before in 2018. Okay. Of course, this is the organic conference, organic workshop. So I briefly mentioned the connection to organics also of this model. This kind of SU4 models are intensively discussed very recently in the relation to twisted barrier graphene carbon systems, because the twisted barrier graphene or even the barrier graphene has spin barrier degrees freedom, and so if you treat this spin barrier model as the, let's say, SU4 spin, then you can discuss SU4 symmetry or the deviation from the SU4 symmetric point. And also, the essential part of my derivation of this model from in this paper is just G1 in strong spin coupling. So we can also consider honeycomb metalorganic frameworks consisting of zirconium 3 plus or hafnium 3 plus forming honeycomb lattice. Then also can be a SU4 candidate. So there is still a room to find organic material or metalorganic material which can realize this type of.
So this SU4 is very specific to honeycomb lattice.
Yeah, very specific to honeycomb lattice.
Only for honeycomb.
Only for honeycomb. And even if the D1 material does not exist, the coordinate realization will help to realize this kind of physics, even if because the coatom with the nuclear spin F has the SU2 F plus 1 symmetry. So for example, we can put ethyl beam or strontium atoms in the laser cooling, and this way people can realize SU6 or SU10 symmetry already, and also SU4 may also eventually be realized too. So by trapping these atoms, cold atoms in the optical lattice, we may also realize QSOL. So there are many routes to realize SU4. That's what I want to say. And this is not a kind of toy model or dream things. The model itself is has a very important as a real system. Then we move on to more theory side. The long-standing unsolved problem for the SU4 physics is, can these SU4 models realize quantum spin orbital liquid or just quantum spin liquid? And the first proposal for quantum spin liquid in the SU4 system was by Juan Vishwanas in 2009. And they proposed the quantum spin orbital liquid ground state for the SU4 Heisenberg on the square lattice. Later, the square lattice was found to be ordered because less frustrated. But the honeycomb lattice is later found to be more frustrated and became another candidate for quantum spin orbital liquid state. This was first proposed by Philip Corbett by using IPEPS or VMC calculation. They proposed a quantum spin orbital liquid state on the honeycomb. However, the real ground state and finite temperature properties have still been elusive for more than decades. So we did reinvestigate this system and give at least partial answer to the problem using new methods called CTPQ and DMRG. And let me briefly review the previous work done by Philip Corbett. And Philip Corbett used the combination of IPEPS, Isgard diagonalization, PMC variation Monte Carlo, and then they suggested a scenario of gap spin liquid for the ground state of the SU4 Heisenberg honeycomb lattice, while there was no unbiased evidence for the existence of a gap or the absence. So today I will propose a different scenario from Philip Corbett. And my scenario is a gap scenario, and this was supported by the calculation of CTPQ and DMRG. And these methods are relatively less biased than other methods like variation of Monte Carlo. So in this sense, I believe that our results are better. And the first thing to show a brief overview of the final temperature results calculated from the CTPQ calculation. CTPQ is a method with a name, a canonical thermal pure quantum states, developed by I think Shimizu and Sugiura-san in the University of Tokyo. The canonical thermal pure quantum state method is a very powerful method to calculate the heat capacity at finite temperature with a small cluster of system. Based on the paper by Nataf and Miller, we newly implemented the exact SUN symmetry in the CTPQ method, which was never done, and allowing the first finite temperature calculation for the SU for Heisenberg and the honeycom. Using a supercomputer, we can compute the heat capacity of the SU for Heisenberg up to 24 sites. 24 sites is very large because if we translate this number to the spin half system, it's 48 sites. So if we count the dimension here in space, so it's a very state of art. This one? So sorry? Yes, that's on the honeycomb. And then,
Question starts to be technical.
Mhm.
So here we have the 24 states, right?
yes, right.
That's to the 48.
Yes.
So why can't we just do ED? Because ED can do precisely 48 spin half states.
But still easy to the block diagonalize this Hamiltonian first by the symmetry. Yes, that's what I did. And I need to go to the final temperature. So ED was already done by Philip Corbo. So I want to go to final temperature here. So
It's only ground state.
Philip Corbo is the same size, 24 size ED.
And which geometry do you use? Are these cubes or?
This one. And 24 sites is very symmetric, so in this sense, it's important size for honeycomb. And but the results are more or less same, independent of the cluster. I did a calculation with 16 sites, 20 sites, 24 sites. And if we plot the heat capacity, they always have a low temperature, large peak of order of 1. And then smoothly goes down at high temperature with a kind of shoulder. So we see characteristic peak and shoulder structure for this model. And also have a kind of sharp drop in the entropy. The left-hand side is the figure of entropy, and the right-hand side is the heat capacity. And or what I want to say is this is very characteristic for this system. So it may be the good signature if for the experiments, but also I found it's because the low temperature gap is very large and also very clear, independent of the cluster size. So, or maybe the ground state is more like a gap rather than gapless. And in that sense, we have to investigate the ground state of this model again with a different method than before. So I newly did the DMRG calculation for the ground state. And as you know, the 2D DMRG is not really a 2D in exact sense, because we use cylinder geometry with a finite circumference fluorescence, but still unbiased, very reliable technique. And in 2D, we use this cylinder geometry as shown here, and the calculation cost grows rapidly about this, exponential about this circumference Ly. But we can do the simulation with a finite Ly, and then eventually we can extrapolate over Ly from the Ly up to 12 sites. That's what I will do from now. this is the technical details of this calculation, but the new thing what I did is nearly fully exploiting the SU4 symmetry completely. So the important thing here is we can go to here I wrote 12,800, but this is the number of states of the SU4 ellipse, and if we if we convert this number to the usual DMRG with U1 symmetry, then this corresponds to 1 million of U1 bond dimension, which is kind of I think the kind of the world record of the DMRG, and without this number we cannot get the results of the new quantum spin. And first, this is the first observation got after the 2D DMRG simulation. The phase diagram is this is written about the Ly, circumference of the cylinder, and I found that the physics or the property of the ground state strongly depends on the value of Ly. If Ly is 4, we see a Lang single phase, and eventually by increasing the Ly, there is a phase function as a quantum phase function as a 1D system, and Ly equals 6, it gets critical, and eventually we can get the gap state over the large number of Ly, 8, 10, 12. I mostly focused on the case larger than 6 because these phases are more interested, but it is how to say very important that we found already a rich phase for the same model with a different circumference of the cylinder. Okay. It's gamma point, I think. Yeah, I think it doesn't matter. That's a very good question. Thank you. Yeah. It must be a gamma point, so it doesn't matter. And first, let me show the largest result of Ly equals 12, and also I will show I will briefly show the results on Ly equals 6. Ly equals 12 is a clearly gapped state. In order to check the gap, we check the entanglement entropy and the spin correlation for the very large 32 times 12 cylinder, and the gap nature is clearly seen from the entanglement entropy, which is the upside of this graph. The upper graph, we have a almost constant entanglement entropy, which is independent of the cut of the cylinder. So this means that the system is almost gapped. And also the lower side is the spin-spin correlation in terms of the distance of two sides. And by increasing the distance between two sides, the spin correlation exactly decays in the exponentially, because this is the log scale. And from these two results, we already saw the signature of gapped state, maybe gapped spin rate. And also I will show a bit difficult figure on the entanglement spectrum. We also check the entanglement spectrum with this kind of SU4 language, but the important thing is that this is essentially the same as what people are doing in the ED as the Anderson's tower of state spectroscopy. And in the same way, I check the kind of Anderson-Tawara state spectroscopy in the entanglement spectrum of this model, but I don't clearly see the clear signature of the symmetry breaking because SU4 symmetry breaking, because if there exists a SU4 symmetry, there should be a clear Anderson-Tawara states in the entanglement spectrum, but the entanglement spectrum still looks random, and this is the first result. We claim that there is no SU4 symmetry breaking. And also, we check the absence of tetramerization or absence of translation symmetry breaking, which means that the absence of the previous order. And for that, we check the expectation values of the bond operators calculated by DMFT, finite DMRG. And this plots the deviation of the expectation value of Pij. Pij is the Hamiltonian bond operator, and the deviation of the bond operator from the average. And the deviation, it's a bit difficult to see, but the value is just, for example, 0.03 or something like that. And in most regions, the magnitude of the deviation of the bond operator, expectation value of bond operator is less than 0.03. So, and also this number is actually exponentially suppressed by increasing the Ly, the circumference of the cylinder. In that sense, the Lang singlet state or BBS order is very suppressed in the large cylinder. And from that, we conclude that maybe in the thermodynamic there should not exist tetramerization or translational symmetry break. And we can obtain the ground state energy by fitting about this LX infinity extrapolation. And error is a bit large, but we get a good number, E over N equals minus 0.9245. And also we can get this number for other system size, and we can do again the extrapolation about Ly. Also, we can get the number of entanglement entropy by the exponential fit of the entanglement entropy at the center cut of the cylinder. We have a mistake. This is not the Ly equal 8, but this is the results for Ly equal 12. But in the case of Ly equal 12, entropy goes to 6.21 in the LX infinity limit, and then we can correct the number of the number of entropy for each Ly, and we can do the exponential again. That's what we will do in the last part. But before that, I first do an energy comparison between the new DMRG and the old work. And by parallel fitting, we obtain the thermodynamic value of energy per site as minus 0.9210, which is the where converged in this, as shown in this figure. And we put the black bar on the top of this graph, which is actually on top of this graph. We also put the black bar of variation of Monte Carlo, the value of the energy per site, and the variation of Monte Carlo gives upper limit of energy per site of minus 0.894. So the gapless Dirac spin liquid observed in the previous work, it has a very large, much larger energy than the value obtained from DMRG. So in that sense, the gapless Dirac spin liquid observed in the previous work may not be the ground state, and we get the lower energy state by DMRG. Okay, 5 minutes. Okay. And as I said, as a supplementary, I will quickly show the results for Ly equals 6, which is not gapped but gapless. in that case, we see the signature of SU for level 1 between criticality. And I did up to 36 times 6 cylinder and do direct extrapolation about the central charge, and the extrapolated value of central charge is 2.9 plus minus 0.1 or something like that. And this is consistent with the SE for level 1 West-Witten, because West-Witten has C equal 3. And in that sense, we can confirm, we could confirm the phase diagram I showed first. And we have the long single phase path, and then it becomes gapless critical with West-Witten criticality, and then gap spin. That's the phase diagram I obtained. Finally, but most important is the calculation of topological entanglement entropy. We put entanglement entropy for different circumference. The data is, of course, without Ly equals 6, because Ly equals 6 is gapless. We cannot put entanglement entropy for that, but otherwise we can put the entanglement entropy for Ly equals 4, 8, 10, 12, and we do the fitting by this function, because we see some oscillation, small oscillation between even a kind of even order effect. And with this even order extrapolation with even order effect, we obtain the value of topological entanglement, which is 1.33 plus minus 3. So this value is very close to log of 4. Log of 4 is 1.386, and this is not exact, but still a very good signature of the quantum dimension of this system. And potentially, this means that the ground state should be the Z4 spin liquid with a topological entanglement of log of 4. My new proposal is the ground state of the SU4 Heisenberg model on the honeycom lattice should be a Z4 spin. And this is the conclusion. SU4 physics contains nice Canonical materials as well as for the atomic realization, and very nice ground state properties with potentially the Z4 spin liquid. And also this is the new route towards quantum spin liquids. And about the realization, I also very recently the collaboration with experiments has just begun. So maybe stay tuned, and thank you very much.